All right, so the first thing I'm going to draw is y is equal to sine x. Okay, and this takes our shape that we're familiar with, goes as high as 1 at how many degrees? 90. At 180 it goes through 0, 270 goes through -1, and 0 at 360. Now if I draw the graph of y equals, so this is what we looked at yesterday. How do these two graphs compare? Somebody put your hand up and let me know. Ophelia.
Well, negative sine x reflects sine x.
Okay, it's a reflection. Now how is it a reflection? Okay, we know it's a reflection, but whereabouts is it reflecting? Yes, Liam.
One line goes up, the other one goes down.
Yes, but I still need, am I reflecting along, let's say, this line? Like if I had to put a mirror in here,
The x-axis.
right, it reflects along the x-axis, okay? If you imagine if I put a mirror in here, it's reflecting these two curves. Is everybody okay with that? Does everybody see what we've got? Hello. All right, let's try exactly the same thing to see if that applies to cosx. Okay, so if I put in y is equal to cosx,
Wait, Mr.
if I put y is equal to cosx and I put y is equal to negative cosx, now I would expect this also to reflect in the x-axis. Does it?
Yeah.
It does, okay? It is reflecting again in the x-axis. So, well, we're not worried about tan, we're only looking at sine and cos at the minute, okay? So, if I put a negative sign in front of sine or cos, I know it's always going to produce a reflection in the what axis? The x-axis. Okay, good. All right, now looking at, so there is y is equal to sine x again. Now if I put y is equal to sine of negative x, what do we notice? What do we... It reflects. Okay, now what is our first impression of where it reflects?
On the x-axis.
It looks like it reflects in the x-axis, so we all agreed with that. It looks like exactly the same. If I actually put in here y is equal to negative sine x, we can see that, what do we notice about these two things, these two graphs? They're the exact same, okay, good. Now, this one's slightly different. Now, if I put in cosx, and I put in y is equal to cos of negative x, it's exact same, okay? Can anybody, now, there is a reflection going on here. But it's a reflection that is producing the same curve. Now, how can I reflect cosx to get exactly the same thing? And it's to do with my y-axis.
Cos negative x?
What type of reflection is happening here? Yep. Let's go back to sine x for a second, okay? So there's sine x, and here is y is equal to sine of negative x. What do we notice about, there's our sine x and there is our sine of negative x. There's a reflection happening in the which axis?
Negative.
Well, it's happening in the x-axis, but I could also say it's happening in the y-axis, okay? This point is being reflected over here. This point is being reflected over here. Yep. This point is being reflected over onto this side. This point is being reflected onto here. So going back to my cosx, is that consistent with this one? Yeah, because this point is being reflected over to here, this point is being reflected over to here, and so on, okay? So if I've got cos of negative x, that produces a reflection in the y-axis, okay? So if I've got the negative inside the bracket, it produces a reflection in the y-axis. If it's outside the trig function, it produces a reflection in the x-axis, okay? So let us copy this down, please. Okay, so we're going to formalize this. We're going to write this down. For each of these, for all of these rules, okay, so I'm going to put down all rules also apply to cosine graphs, okay? So I'm just going to put the rules for sine, but it also is exactly the same for cosine, okay? So we can just quickly do a little sketch. So there's our y is equal to sine x. Y is equal to negative sine x. Reflects this in the x-axis, okay? So this is our x-axis, y-axis. So it is being reflected.
You mean pi or
And we'll do a little diagram actually for cos as well. So I just want a little sketch. And if I'm reflecting cosx in the x-axis, try and do it as neat as possible. And again, you can check them on Desmos. Gents, shh, focusing please.
the balloons? Negative sine x, right?
Yeah. All right, if I want to reflect, now, so to draw y is equal to sine of negative x, I need to reflect this curve in the y-axis, okay? So to do that, this point is going to be reflected over here. So it's going to come up. This point is going to be reflected over here, okay? So it's going to come back down here, back up, and so on, okay? So this blue one is y is equal to sine of negative x. Now you need to remember these rules, okay? And I'll draw the same again for cosx, but what do we remember about cosx?
The same.
Yeah, it's going to be the same. Okay, they're going to be exactly the same because this point is reflected over here. So these are exactly the same curve. Okay, the next part is, so that was reflection. This bit is translations.
So this is part 2.
Yeah. All right, and I'm going to say for y equals sine x, the graph of y equals sine x plus d produces a translation of y equals sine x of d units vertically. So remember when we did these, okay? If I show you another quick example, so let's draw. Yep. Is that okay? So if I was to draw sine x, if I was going to draw sine x plus 1, what happens?
It goes up 1 unit.
Yeah, it goes up 1 unit. Okay, the whole thing goes up 1 unit. Goes up 1 unit. If it was sine x take away 3, what would happen? The graph, it would go down 3 units. And again, this is exactly the same thing if I'm dealing with cos. So, you okay, Zaire?
Yeah, I was asking, is there anything that could use with those?
Yes. So remember, these are just sketches that I'm doing. I was going to draw y is equal to cosx, take away 1, or take away 2 even. It's not a very good diagram. Let me just move this down a little bit.
So it's y equals cos 2. Oh, x plus 2.
Let's move down, so it's, I've moved it down 2 units, okay?
Oh, negative, right.
So the whole thing is shifted down 2 units, yep. So the final type are called dilations. So remember we were talking about a vertical dilation or a horizontal dilation. Okay, so I'm going to write for y is equal to sine x. The graph of y equals a sine x produces a, so the posh mathematical way to say it, produces a vertical dilation of scale factor a parallel to the y-axis. Can anybody tell me what that means in normal words? Or even, like, what does it do to the graph? It stretches it, right? And it stretches it vertically. Vertically, okay?
Oh, it'll be more arced, kind of?
So it's kind of just goes like, stretches it up like
Like
that.
that?
Yes, yeah. Exactly, good.
So just like the amplitude is bigger?
Yes, and it makes the amplitude bigger, good. So again, just to kind of do a quick sketch. Now remember, we're just doing sketches. Keep them neat. Neater than me. So if I've got y equals sine x, and let's say I'm going to draw y equals 2 sine x. How high does sine x go, remind me?
Starts at 0.
It goes up as high as,
1.
and goes as low as -1. So if I'm going to draw 2 sine x, it's going to go as, yep, up to 2 and down to -2. Keep it nice and neat.
Let's just say 2 sine x has more of a
It does. And I'll do one for, how high does cosx go?
1. -1.
Yep, it goes up to 1, down as low as -1. So if I was going to draw y equals a half cos x,
We go to 0.5.
it would go to 0.5, right? So it would start at 0.5. It would only go as low as 0.5 and then back up to 0.5, okay? Well, it's still a dilation, but we haven't really. So that's the amplitude. The other one was the to do with the period, which is the frequency. Okay, so for y equals sine x, the graph of y equals sine bx produces a horizontal dilation of scale factor one over b parallel to the x-axis. And we said b is the frequency. How do we work out the period if we know what the frequency is?
Is half another.
It's
a cycle.
yeah, it tells us the number of cycles, but b tells us the number of cycles. But to work out the period, it's 360
Divided by the number.
divided by b.
By b.
Okay, divided by b. Frequency. Too far?
Yeah.
This is the last bit, and then we'll be good. Sorry. What about that?
Yeah, that's
Yeah.
Okay. Right, okay, so that's y is equal to sine x. If I wanted to draw y is equal to sine 2x, what's it gonna look like? Or who can tell me how to do that? Not go up by 2, so it's no. It squishes it. So how many sine graphs do I need to fit in between 0 and 360? I need to fit in 2. So between 0 and 80 I have to have 1. Okay, that's really messy. Let's make that hopefully a bit neater. No, don't do that. Okay, it's all going wrong.
All right, because you.
There's 1, and then the other one. 2, okay? So you're trying to fit in 2 sine graphs in between 0 and 360. What is the period of sine 2x?
90? Oh, wait.
No, it's 180.
It's
Yeah, 180.
180 because it starts to repeat after
Yeah,
180
it's divided
degrees.
by 2.
Okay, apologies for that's a little bit messy there. I'm going to try and draw that again. So 1 sine graph, 2 sine graphs, and it starts to repeat at 180. And let's just put in one more. Let's do cos example. There's a lot going on here. Of course you can. I wouldn't be doing it if I didn't think you could handle it. Okay, so there's y is equal to cos x. If I wanted to draw, I'm going to make this one slightly harder. let's say cos a half x.
It would only go down and then stop at what, -1?
Well, yeah, I know what you mean. How many?
It would repeat, it would do one of those every 0.5.
So remember, for sine of 2x, I fit 2 sine curves in between 0 and 360. How many cos curves do I want to fit in now between 0 and 360? A half of a cos curve. So I only want to fit in that much, okay? So it's going to go... It's only half of a cos curve, okay? So what is the period of this one then?
Ooh, 720.
Right, good, because one whole cos curve is going to occur in 720 degrees. Good. And remember, you can work that out as well by doing 360 divided by a half, which is 720 degrees.